Today, caching, the trick that makes slow systems feel instant and the one that sometimes breaks them in spectacular ways. Your app was perfect with 10 users. Now it has 50,000 and every single one is asking the database the exact same question thousands of times a second. The database is sweating. Something has to give. Here's why this matters. Reading a value from memory takes about 100 nanoseconds. Fetching that same value from a spinning hard disk takes about 10 milliseconds. That's roughly 100,000 times slower. Every trip to slow storage is time your users spend waiting. Most systems start simple. A request comes in, your app server asks the database for the answer and sends it back. Clean, correct. And for a while, completely fine. Then traffic grows. The same expensive query runs again and again for data that barely changes. The database becomes the bottleneck, the one component everything else waits on. Add more app servers and you just send it more work. The fix is a cache. A cache is a small, fast storage layer that keeps copies of frequently used data close to where it's needed, usually right in memory, so you can skip the slow trip to the source. Ask once, remember the answer, reuse it. Think of a busy library. Behind the front desk, the librarian keeps a small shelf of the most requested books, today's bestsellers, the ones everyone wants. Everything else lives down in the basement archive, complete, reliable, and slow to reach. That front shelf is your cache. The basement is your database. Here's how it works in practice. The pattern is called cache aside. When a request arrives, your app checks the cache first. If the data's there, a cache hit, it's returned instantly. If it's not, a cache miss, the app reads the database, stores a copy in the cache, then returns it. The first request pays the slow cost. Everyone after rides the fast path. Writes need a plan too. With write-through, you update the cache and the database together so they stay in sync. Safe, but every write pays both costs. With write-back, you update the cache now in the database later. Fast, but if that server dies before it catches up, you lose data. There's no free lunch. But that front shelf only holds so many books. When it's full and a new request comes in, something has to go. The most common rule is least recently used, or LRU, evict whatever hasn't been touched for the longest. You can also give each entry a time to live, a TTL, so it expires automatically after a few seconds or minutes, popular or not. Now the dangerous part. The basement gets a new edition of a book, but the copy on the front shelf is still the old one. Your cache is now serving stale data, an answer that used to be right and quietly isn't anymore. Fixing that is called cache invalidation, removing or updating the cached copy the moment the real data changes. And caches aren't meant just one box, they live at every layer of the stack. Your browser caches images and files locally, a CDN, a content delivery network, caches them in cities near your users. Your application keeps a shared in-memory cache like Redis. Even the database caches its own recent queries. Each layer catches requests, so fewer reach the slow core. Now the part everyone gets wrong. Most people think the hard part of caching is making things fast or deciding what to store. It isn't. The hard part is invalidation, knowing exactly when a cached copy has gone wrong and getting rid of it. There's an old joke among engineers. There are only two hard problems in computer science: cache invalidation and naming things. It's a joke because it's true. And invalidation has a nasty failure mode. Picture one wildly popular book. Its copy on the front shelf expires. Now every patron who wants it misses at the same instant, and they all stampede the basement at once. That sudden flood is called a cache stampede, or a thundering herd. The very database you are protecting gets buried under the requests you cache to avoid. This isn't hypothetical. In September 2010, Facebook went down for about 2.5 hours, its worst outage in years. The trigger was a single invalid configuration value. Every client that noticed it tried to fix itself by querying the same database cluster. That overwhelmed the database, which made every client fail and retry, a feedback loop that kept the system down even after the bad value was corrected. To recover, engineers had to stop all traffic to that cluster and let it breathe, a classic stampede at global scale. So what actually does this in the real world? For in-memory caching, Redis and Memcached are the standards. For caching web responses, Varnish and NGINX. CDNs like Cloudflare, Fastly, and CloudFront handle the edge. They're all battle-tested. You almost never build a cache from scratch. But a cache is never free. You're trading freshness for speed. There's always a window where the cached answer might be out of date. You're adding a second source of truth that can disagree with the first, and you're adding moving parts, eviction, expiry, stampede protection, that all need tuning. Cache it when reads dominate and slightly stale is acceptable. Don't cache data that must always be exactly right. Quick recap. A cache is a small, fast layer that stores copies of hot data, so you skip the slow source. Reads get faster, your database gets breathing room, but you take on staleness, eviction, and invalidation as the price. The takeaway: caching doesn't remove work. It moves it to the moment your data changes. Now I want to hear from you. What's the longest TTL you'd trust on real production data? 1 second, 1 minute, 1 hour. And what kind of data would you absolutely never cache? Tell me below and tell me why. Next episode: what happens when one database isn't enough and you have to split your data across many? Sharding and the headaches it brings. See you then.